section 5.3. There's a little bit of stuff you've seen and quite a lot that you've not. So first thing we're going to look at is the fundamental theorem of calculus, part 1. We're going to look at an area function, then that, and then we'll look at the fundamental theorem of calculus, part 2, which you've actually seen. And then the rest of today is going to be all about finding antiderivatives, how to find the shortcut for the area under a curve. So first things first, let's look at this guy called the area function. So imagine you've got a curve called y equals f of t. So this is the t-axis, not the x-axis. So you get y equals f of t, and it starts at t is a and it finishes at x, and we want to find this area. Well, the area function g of x is defined to be the area under the curve starting at a and finishing x. In other words, this area here, called the area function. So let's, you don't get much. I think you get 2 questions on the area function directly. So let's use the area function and calculate it. So this ziggy-zag thing is going to be my function f of t, this red guy. And so the area function is going to be the integral from 0 to x, because in this case, you're starting at 0, t equals 0, and you're going to, I guess, finish at 12. And 0 to some point x, that's g of x, of, well, the area under the curve. So let's skip this one for a second and do g of 2. If you want g of 2, is the integral from 0 to 2. G of 2 is that guy. And if you count units, it's 2 units by 4 units, so that guy is 8. Now suppose I want to do g of 4. Well, g of 4 just ends up being all of that. Now we can save a little bit of work, because if you already know this piece here is 8, don't we just need to find this piece and add it up? So if you want to save your workload, use previous answers to help you. Now, this shape here, you could tackle it lots of ways. I would probably do a box, which is worth 8, and a triangle, which is what? 2 units by 6, half of 2 times 6 is half of 12, so it's 6. So that guy there, right, plus that guy there. So you've got 8, plus these 2, which is 14. So the answer is 22. Are we comfortable about how, if I give you a sketch like this, you can find the area function at various points? Right. Let's find out with g of 6. So g of 6, I'm going to just change my shading scheme. So it's the area under a curve from 0 to 6. So won't it be this guy, which is 8, plus these 2 guys that add up to 14, and then just add this extra little triangle at the end. So what's that guy? 2 times 10. So half of 2 times 10 is 10. So that guy would be 32. Now we're going to make life really awkward for you on the next one. The area under the curve starting at 0 and finishing at 10. Well, it's going to be 32. Nothing wrong with that. That's all the stuff up to that. And I've got a little triangle here. And this is 4 and this is 4. Might not look at it, but that's 4 units and that's 4. So half of 4 times 4 is 8. But then we have to be really careful. What's special about that 8?
It's negative because it's below the line.
Great. So when this one gets done, do you see our answer is actually going to be a little bit smaller. It's going to be 24, I believe, right? And I don't have time, but couldn't I do 12 as well if I wanted to, right? Wouldn't I just take away another, what's that, 2b4, another 4? So what you have created here are little snapshots of the area function. Now, I missed this one at the start deliberately because it's kind of a trick question. when you're asked to find the area function at 0, isn't that the area from 0 to 0? You guess that's a little bit weird. Would you agree that the answer is 0? That makes sense? So that is an area function. Is there any questions about how you would calculate it? You know, how you would get all the various guys? You know, does that make sense to you? Okay, so let me show you the 2 questions. I believe it's 2, where you're asked to calculate specific values of an area function. Right, here's question 1, this guy. And can you see you're going to be asked for G of 0 and G of 30. Be careful of the scales here. It looks like the scales are 5, 10 and 5, 10. So watch out for scales, right? Don't just count boxes. You'll get caught out if you do that. So if you were doing this one here, right, G of 5, for instance, it would be a rectangle 5 units by 10. So that would be 50. So that guy there, for instance, would be 50, right? So watch out for that. Now, it goes on and it asks you things like, when is it increasing and decreasing? Well, if you've got these numbers, you should be able to tell. Doesn't this function get bigger and bigger till you reach 15 and then it reduces after that? And one of these graphs is going to represent what that function would look like if you plotted it. Now, you won't be able to do a perfect curve, but can you imagine you plotted all these guys? Couldn't you draw a little curve through the dots, and that would be one of these fellas? And I am picking that one. Why is that the graph of G of X? If you plotted the area function, why am I picking that one rather than, I'll shrink it down now, rather than pick, say, that one or any of these 2? There's just one thing that made it, as far as I was concerned. Well, I guess there's 2 things, but why I chose that one.
Is it because it starts at 0?
Yep. Now, so does that one. But why am I picking that one over that one? Because they're the only ones that start at the origin. Why is
Value increases until 15 and then decreases.
Yeah, and it's positive, isn't it? And weren't all our numbers positive? The ones we calculated in my example would be very similar to that one. And there's another one.
Quick question just on
Yes.
the part that says the interval notation. Does it just want something like 0 is less than or equal to X is less than or equal to, say, 15?
They want the other version, that it might accept that, but it wants the one that looks like a coordinate. So let's say it was increasing from 0, to 15. That would be interval notation.
Okay, awesome. Thank you.
If you were doing the one you just mentioned, it might accept it, but it would look something like this if I caught you correctly. Is that what you were thinking, the other one?
Yeah, that's what I was thinking, but the other one makes sense.
Okay. Question 2, same kind of idea. Right. And that is the end of what you would be expected to do numerically with an area function. So that's kind of cool. We got one out of the way. So I'll move that off my little list. I feel like one of those people in the TV shows that say, here's one I prepared earlier. Here's number 2. Actually, I prepared it from my other Calc 2 class, so it seemed to me worth it. Now, this is the second topic we're going to deal with, and it's called the Fundamental Theorem of Calculus, Part 1. And what it says is that the area function, right, G of X, the area function, has a very interesting property. If you can get the formula, right, for an area function, G of X, if you differentiate that function, here's a remarkable thing, or maybe it's not so remarkable. Do you see that you get f of x? I'll show you how that works. It's actually, a lot of people make this harder than it should be, right? I guess they overthink it. Suppose I gave you an area function and it looked like this. The integral from 0 to x of t squared plus 1 dt, right? Suppose that was my area function. According to the fundamental theorem of calculus 1, its derivative, whoops, is x squared plus 1. Now, if you think about it, isn't f of t that guy? So isn't f of x just that guy with an x? Try another one. Suppose the area function was the integral from 0 to x of sine t over t, right? What would the derivative of the area function be? And remember, the variable has to be x.
Sine x over x.
Yep. Do another one. Suppose the area function was 0 to x of the square root of e to the t plus t. I'm just randomly picking whatever I feel like. It really doesn't matter what I randomly pick. Do you see the answer is very, very trivial? Do you see what the answer is going to be? It's going to be the square root of e to the x plus x. Now, have you noticed that these three all started with 0? See, if I stuck a 10 there, it would make no difference at all. The answer would still be x squared plus 1. And you might think, well, if you start at 0 and you start at 10, you're going to get different functions. The only difference between the two functions is a number, right? It's like the value at 10. And is it a number when you differentiate it disappear? So it doesn't actually matter. You can make that 0, you can make it 10, you can even make it an arbitrary number called a, and not even tell people who a is. Do you see that the derivative of the area function really doesn't care? It has no effect on it. Are we cool with that? For such a big name, the fundamental theorem of calculus part 1, you would think it was something big. Wouldn't you think it's something you're going to use a lot? You don't. It's actually the fundamental theorem of calculus part 2. We've already seen that guy. Remember the antiderivative guy? That's actually the guy that you use. That's the guy that is helpful. Okay, let's take a look at some of those questions. And here we go. So I'll make these nice and big because I don't know what kind of screen some of you have got. I think big is better. Okay. What would the derivative of that area function be?
The square root of x to the 4th plus x to the 6th.
Agree? How about the derivative of this area function? Natural log of 8 plus x squared. Oh, I don't think this should throw you. Do you notice that they're using the variable w now instead of x? So what would the formula for g dashed of w be in this question?
Sine of 8 plus w to the 5th power.
Right. Try to get away from thinking x is the only variable in the world and that calculus can only have x's and x cubes. You know, those variable letters are just placeholders. You can use any letter of the alphabet, but we typically use x or t or w. You know, we tend to keep to the later letters, but that's about all. And that is the end of the fundamental theorem of calculus part 1. Its 5 minutes of fame are now over. Everything that we're going to do from now on either uses directly or indirectly the fundamental theorem of calculus part 2. So suppose you want to find the area under a curve f of x from a to x equals b for a well-behaved function. That just means that it's a nice function, right? You don't want to try and find the area under a function that's got a vertical asymptote on it, right? That doesn't end well. You don't want one of those functions with holes in them and, you know, there's weird stuff happens, right? So we cover ourselves and just say, it's a nice function, well-behaved. It's continuous, it's differentiable, it doesn't have any discontinuities, all that good stuff. Well, according to the fundamental theorem of calculus part 2, if you want to find the area under the curve from a to b of a function f of x dx, it's capital F of b, the antiderivative evaluated at b, take away the antiderivative evaluated at a, where capital F of x is the antiderivative. And here's a little side note. Do you know what the derivative of an antiderivative is? The guy you started with, f of x. And that's why we call it an antiderivative, right? It's the opposite of differentiation. Does that make sense? And you can think of this capital F of x as actually the area function. Remember the area function that we did at the start of today? Capital F of x, the antiderivative, could be thought of as the area function. Are we good with that, guy? Right, for the rest of today and definitely tomorrow, we are going to focus on finding areas under curves. Well, either that or at least finding antiderivatives, right? A bit of A, a bit of B. So if someone said to you, I'd like to know the area under the curve from 1 to 2, and it was for x squared plus 4x minus 1. The way that we do that question is we find the antiderivative of this function. And we're going to use a guy called the power rule. And what the power rule allows us to do is to find antiderivatives of powers of x. So it's written down as a formula that says any multiple of a power of x, its antiderivative is add 1 to the power and divide by the new power. That's an n, by the way. There we go. So I think of it as English. I just say add 1 to the power, divide by the new power. This one. Add 1 to the power, divide by the new power. What would -1 get you? That's always a tricky one for some people until they get used to it. Antiderivative of -1.
Negative x.
Negative x. Now, we will not put plus c's on these. And the reason you don't put plus c's is they're kind of there, but you don't put them in because they're going to kill each other off, right? It's kind of laziness, but it's a cool laziness. So this is the antiderivative. This is the guy we would call f of x. Now, wouldn't we find f of 2 and then subtract f of 1, right? That's what the formula says we should do. The way that we set out our working is everybody draws a big vertical line and they put x equals 1 and x equals 2. And that's just saying, look, I'm going to evaluate this at these 2 points. So if you plug in x is 2, that's what you get. That's basically what f of 2 is, right? And then you take away what you get when you plug in 1. And that's basically take away f of 1. And do you see this notation just makes it a little bit easier to write down what you're doing? That's all it's there for. Right, so this vertical line x equals 1 and x equals 2 is so that we do this line, right? Just a way of setting it up. Now, I'm doing this a lot more lines than you would ever need to, even in a test. But that's 8/3. That's 2, 4, 8. Take away, don't know why I called that x, it's 2. Take away 2. Subtract, that's 1/3. That's 2. Take away 1. This guy is 6, and that fella there, so I guess I'll leave him alone. It's 8/3 add 6. Take away 1/3 minus 1. And That guy and that guy gets you 7/3. 7/3 plus 5. 5 is 15/3. So when I'm finished, it's 22/3. So we have now got the exact value. If you're good at the calculator, can you probably go from there to there in one go? Now, I would like to check that this is correct. So let's show you a little trick you can do. You go y equals, and you type in your function. So in this case, it's x squared plus 4x, take away 1. Then you do your window, in this case, from 1 to 2, which that one is. I then do zoom 0, zoom to fit. Pretty boring curve, isn't it? It's almost a straight line. And then you go second calc. And the guy you choose is number 7, right down at the bottom. And it's going to ask you for the lower limit, which is 1. You press enter. Then it's going to ask you for the upper limit, which is 2. And then you press enter. And you see that answer there? The 7 point all the 3s? That's this guy. And now I can check. Is 22 divided by 3? You see it matches. Now it's easier in WebAssign. Don't you just plug that into WebAssign and it does a big check mark or a cross? But if you do it this way, don't you know what your answer should be as well? So if it doesn't match, and I did this with the earlier class, I think I put something like 23/3 down because I didn't add them right in my head. And I'm almost there, right? You know, a little bit out, and I figured out, you know, somewhere around here I forgot to add it right. Away go. Right. I'm not, before I forget, whenever you are doing an integral, that's what we call these, right? This area under curve questions, these integrals. If there are limits, right, numbers from 1 to 2, these are called definite integrals. And we'll do a lot of these, but tomorrow. We are going to look and focus on these fellows instead. In some ways, indefinite integrals are going to be quicker, because in an indefinite integral, you do not get what are called limits of integration, right? You don't get numbers like 1 and 2 here. So when you do this guy's answer, it's going to be that fella plus this guy plus this guy. Plus what else? What do you always have in an indefinite that you don't bother on this side?
Arbitrary constant.
Let's see.
Let's see. Right. So can you see in a lot of ways, isn't there a lot less work on the indefinite ones? Because I want us to get good at finding the indefinite integral, because isn't this just number crunching after that? Don't you plug in 2 numbers and subtract? You know, most of that's going to probably get done by your calculator anyway, right? So the algebra side is doing these. So we are going to do some, and we've got a little list. I'll probably write it down as we come across it. So where shall I go next? How about the integral? Isn't this a power rule? Isn't the only difference my answer is going to be powers of t instead of powers of x? So I'm trying to get away from you just thinking everything's an x in the world. It's not. Now, if you add 1 to the power, you get t to the 4. Dividing by 4 is the same. Well, in this case, I don't need to. It's the same as multiplying by a quarter. And are you happy about the 1/3? Now, can you always check? You all know how to differentiate. If you differentiate this, don't you get that? Isn't that a good quick check? if I differentiate this, do I get back where I started? If you say yes, you know you've done it right. Now in this one, you're going to add 1 to the power. Dividing by the new power gets me a 6th. And the 3 is just going to get me 3t, and I'm going to put a plus c. And hopefully you're all happy about that. Right? Power rule. How about this fella? I'll go back to x's now. I have a problem with trying to find the antiderivative of this, and the problem's caused by the square root of x. It's not written in a format that's going to make it easy for me to use a power rule. So this brings back some algebra. I'm sure we've done one like this before somewhere. How will I rewrite the square root of x so that it's in a form that's going to make this work?
4x to the negative half power.
Is it negative half or positive?
Positive.
Now, in this format, I can add 1 to the power. Now, dividing by 3/2 is the same thing as multiplying by 2/3, and that's how I get that. And although that might work in WebAssign, we're not going to stop there. I'm going to use style points. And in integration, one of the major rules is make your answer look like the original. Didn't this question begin life as a square root? Shouldn't it end its life, right? The answer should look like it. And when you get test questions, this is what I'd expect to see. If you stop there, I'm taking a point or 2 off. Not because it's wrong, but because it's not 100% right. Isn't that the answer we want to see? And there are good reasons for that. Now, I can't help what WebAssign does. It's, you know, I have no control over them. If I ever talked to the guys who program it, I'd probably tell them, will you stop allowing this as an acceptable answer, right? So that everybody does it. But we need to have consistency in math so that if you're French or you're Chinese or you're German or you're from Nigeria, wherever it is you come from, everybody ends up writing the answer in the same format. Can you see? Consistency makes it easier to compare. And now, as things get uglier and uglier and uglier, isn't that probably going to become more and more important? Because if we all end up at the same answer, it's dead easy to check. But if we all end up with maybe the same type of answer, but in 5 different looks, aren't you going to have a hard time checking everybody's work? Because you're forever going to, well, does that mean the same as this? I'm going to have to change that into a square root. Yep. Okay, it works. We don't want that hassle. Here's a different puzzle. Still on power rule. Help us out here. Help your fellow classmates. What would you do here?
We're gonna factor it out first.
I agree. Can you trust me after I foil, it looks like that? I'm saying that, yes, it does. Yes, it does. I did double check. Now, when it gets to here, isn't it basically just a power rule? Right. And I have an x cubed, so right, add 1 to power, divide by the new power. Add 1 to power, divide by the new power, blah, 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 all that stuff. I think the power rule is pretty straightforward, so I'll just zoom through that part. Uh-oh. Sometimes the smallest looking ones can cause you the most headache. What in heck is that going to have to turn into? because I definitely can't use a power rule on it right now.
Uh, 10 times x to the negative 1/3 power.
We feel good with that? Right. Now, power rule, even if it's ugly, still works. Add 1 to the power, you get positive 2/3. Divide by 2/3 is the same as multiplying by 3/2. 10 times 3/2, I believe, gets you 15. Will you double check that? Because I'm doing it in my brain. Is 10 times 3/2 15? I believe it is, but somebody know it. I got a thumbs up, I'm going for it. Plus C. And just say it yourself every time you do a question. Style points. Because maybe it's ready, maybe it's done, right? Style points. Does that guy look done? Okay. X to the 2/3 has to be written down in some kind of form that is a radical, right? It's either the cube root of x squared or the square root of x cubed. That's probably the only two choices I can think of, but one of them's right. So which one is that? Square root guy or cube root guy?
Cube root.
Correct. How do you know it's the cube root? Apart from, I guess, that's not allowed.
Because the bottom number is usually the one that's the root.
It's always the one that's the root, right? Always.
Yeah.
Okay. Are we cool with that now? How about this fella? I like these. I like questions where you have to think. I like puzzles. Maybe that's why I like math. Here's a puzzle for you. Any suggestions for how to solve the puzzle? What should I do?
Turn the square root of x to the power of 1/2.
I like it. Anybody else want to continue? What do we do now?
Now we're gonna multiply our other operation by x to the 1/2. Spread that.
Right, so you're going to have to bring a skill that you might have got rusty at because it's so long you've done it. If you multiply x squared by x to the 1/2, no, the answer is not x to the 1. Agreed? It's not x to the 1. Don't you add the two powers together. Now, it's easy when it's x squared and x cubed, you end up with 5. But when it's x squared and x to the 1/2, you don't end up with 2.5. You end up with 5/2. Are you comfortable about why that's 5/2? X to the square, x to the 1/2, add the powers, 2.5 becomes 5/2. So this guy is 5/2. And this guy is just a 1/2. So do you see in this question, it took us a couple of steps before we got to the, I can now use the power rule. Add 1 to the power, you get 7/2. Divide by that's the same as multiplying by 2/7, so that's where that guy came from. Add 1 to the power is 3/2. Divide by the new power. It's like multiplying by 2/3. And then do a C. And then say style points. 4/7, the square root of x to the 7, plus 2/3, the square root of x cubed, plus C. Now, another advantage to doing style points would be if you're actually going to do a definite integral. If someone went and said to you the integral from 0 to 1, wouldn't you still do that? I mean, the only piece you would probably not need is that. Technically, couldn't you put it in and it wouldn't matter? Because later on it would cancel out with another one. But, you know, now, when you have the guys, well, maybe one's a bad choice. I'll make that 2. That's better. When you plug 2 into this, you'll get 4 7s, 2, 4, 8, 16, 32, 64, 128. And 2 thirds, 2, 4, 8. Take away whole load of nothings, take away a whole load of nothings. So can you see that that answer, I know you might be able to tidy it up a little bit, but is it that one at least well on its way to being finished? On the other hand, if I'd left it as 7 halves, would you agree that is a very weird looking answer and probably wouldn't make a lot of sense to most people? Would you agree that this answer just looks cleaner? You can tell roughly what you're doing, right? Now, couldn't it get even worse if you started with cube roots and negative numbers and all sorts of other things going on, right? So keep the thing, style points tends to make calculations at the end as well, relatively easy. Okay, next guy in my list. Again, this is kind of review. What is the antiderivative of cosine x?
Negative sine x.
Okay, let's double check it. If you differentiate negative sine x, what do you get? Okay, you want to change your mind? And I'm pretty sure you're just going to change the sign, right?
That's right, just sine x.
So what is the antiderivative of sine x going to be?
That one is negative, cousin.
That one is negative. Isn't it kind of the reverse of differentiation? But isn't antiderivatives the opposite? So maybe that's not such a big surprise. So suppose you were being asked to do the antiderivative of that guy. Well, when you do a sine, you get a negative cosine. And when you do a cosine, you get a positive sine. As long as you've got a good memory, that's pretty easy, isn't it? Okay, let's make life awkward. Suppose I was doing that one. Well, when you find the antiderivative of cosine, it is sine x. What is the antiderivative of negative sine x? Be careful. Antiderivative of negative sine x.
Positive cosine x.
Isn't it the negative of a negative, so you end up back with a positive? Right, so just keep track of those. Secant squared x. Antiderivative. What function, if you differentiated it, would get you secant squared? That's what an antiderivative is.
Tangent
secant
x.
times tangent.
Well, I had two, but the first one I heard was tangent. And that's the one I wanted. Agreed? So if you want to do this guy, isn't the answer just 3 tangent x's plus c? The power rule has lots of different variations and flavors, right? There's a lot of mileage in the power rule. Would you agree that these trig ones are kind of, once you've got them, all you do is multiples of them? You know, 3 of this guy, 2 of that guy. There's not too much more, although there is a few things we haven't done yet that you can do with them except that. But that's fine, they do what they do. Now, total change in tack. Antiderivative of e to the x. My favorite function, yeah, my favorite function.
E to the x.
It's one of the few functions I tend not to screw up. I have been known to accidentally get these two mixed up, or I should say these two. Yeah. Isn't that because sometimes you're differentiating and then sometimes you're integrating, and when I teach, sometimes I'm teaching a Calc 1 and then right after it I'm doing a Calc 2. So you can see for my brain, that switchover can happen quite quickly, right? For you, you know you're working in one world, right? Right now you're on the antiderivative world, right? So it's a little bit easier once you've done a few to get into that mindset. This fella is simply just that, right? Would you agree there's not an awful lot you can do right now to e to the x, right? 2e to the x, a half e to the x, but not much. So I'm about to give you a trick question. I've deliberately gave you a trick question. What's its antiderivative?
One-third e to the k root.
I-
Or the k-
I managed to, I know what you're saying, Sabrina, I managed to catch it. And I did say trick question, didn't I say something like, well, I'm going to say it now. Danger, Will Robinson, danger. What you did is very normal, it's very natural, but it's not right. Think it through again. E squared.
Is it e squared times x?
What do you think, Sabrina? Do you see how easy it is to be in a mindset where e to the x is e to the x? So the minute you see an e, you just stop looking, which is very easy to do. I'm sure I'll do that sometimes in the future as well, right? Well, wait a minute, I never make mistakes, do I? That's right, I forgot about that for a minute, I'm perfect. Be cool on this guy? We'll try another one then. Danger, Will Robinson. Danger. What is the antiderivative of that guy?
It would just be the square root of 2 times x, but you got to be really careful not to write it so it looks like the x is under the square root.
Oh yeah, I put a little, sometimes I put a little kink on the square root to try and remind myself. And I guess you could do that if you're really stuck. Let's do this one by a number as our last question. Suppose I wanted to know the integral from 1 to 3 of the square root of 2 to x. Then its antiderivative is square root of 2 x. Evaluated at 1 and evaluated at 3. Well, when you plug in 3, you get 3 square root of 2's. Take away when you plug in 1, you get 1 square root of 2. And do you see the answer comes out really clean? I was going to make that the last question, but I've just thought of one even better. This is a twofer. This question is going to have two parts. This is the first part. I know the answer to that without doing any calculus at all.
Is it 0?
Yeah. Why is it? You're right. What made you think 0? Even if I can't draw well.
Because the sign of 2 pi and of 0 are both 0. So 0 minus 0.
Oh, that's true. Do you notice that this piece and that piece are the same size but opposite? And if you do that, won't they cancel out and get 0? This is the second one then. I know the answer to that one without using calculus. And pretend I can draw better. If you put it into your calculator, that's what sine of 2x would look like. You know how it repeats itself twice because it's 2x. What's the answer to that one?
Zero.
Agreed. I know they don't look at that's because I can't draw, but won't the two bumps cancel out the two happy face shapes? Remember, above is positive, below is negative. If the shape above is the same size as the shape below, won't the answer be 0? So say hi and bye-bye. We learned some cool stuff today, didn't we? Oh, a thumbs up. Thank you, Sabrina. I like thumbs up.
Bye. Have a great rest of your Monday.
Bye-bye. Bye-bye, Alexander. You got a great name there. I'm thinking of giving you 5% on your grade. I probably won't, but I'm thinking about it.
Yeah, well, have a good day.
You too. Bye-bye.